Hey guys. Alright, so this is the second part, 5.2, topic 5.2, in the unit of thermal chemistry. So today we're going to be talking about Hess's Law. Obviously, this is some dude named Hess, and he figured out something. Something important, I guess. Well, for section 5.1, we learned about, the introduction of thermodynamics. That every reaction can either be exothermic or endothermic. How can you tell? Well, do the reaction itself. If it gives off heat, it's exothermic. If it doesn't give off heat but it turns cold, that's endothermic. Pretty simple. Quantitatively, delta H, which is the change in enthalpy of a system, will be greater than 1, will be positive if it's an endothermic reaction, and it will be negative if it's an exothermic reaction. Okay? The number itself is measured in kilojoules, so you can pretty much bet that the larger the delta H is, the more energy it will either emit or absorb, depending, if it's exo or endo. To test that, we built a calorimeter. That was easy to do, right? A couple of styrofoam cup, a stir stick, a cover, and most importantly, a thermometer. Because in order to find out how much energy a reaction needs or release, you look at the difference in temperature. But dang, what if that is not possible to do? What if you have a reaction that you want to find delta H for, but you can't use a calorimeter? What do you have to do? Well, this is the whole idea of where Hess comes in. This is going to be a 2-part lesson where we're going to look at Hess in terms of what he's discovered. So let's take a look at this. Basically, is a reaction that is being carried out in what we call a stepwise reaction. That's right. Not every reaction is a single reaction. Most reaction, especially when you're talking about biological pathways, when you go from glucose to pyruvate, you don't know. It's a series of reactions to do that. It's not like A plus B will give you C plus D. No, that's what you're hoping for. You're hoping to do a reaction where you take A plus B, and this will go through some sort of double displacement or something to give you C plus D. And you want to know what is the delta H for that. You want to know if that will be exothermic or endothermic. If it is, how much, man? But you can't. Because this reaction doesn't play that game. It has what we call an intermediate. And that intermediate is called XY. So in order for A and B to become C and D, they have to go through this intermediate called XY. So let's just say A plus B will react to give you X plus Y. And that has a certain delta H. To follow along, very soon after, X and Y will get together to give you that C plus D that you wanted. This reaction, which you can call step 2, has its own change in enthalpy. Let's call it delta H2. The sum of the two steps will equal to that delta H that you wanted. Hence, this guy right here. So A plus B gives you C plus D is the sum of the two delta H's intermediate. That's exactly how it works. Now, of course, I can do this a little graphically, sort of give you a little rundown in terms of what's going on. So A plus B, gives you your desire is C plus D, that has a certain delta H. But, well, life is not simple. Okay, A plus B will have to do a little detour to give you X plus Y. This reaction has a certain intermediate called delta H1. Then X plus Y can go and give you C plus D, which has another intermediate, of course, of delta H2. Or change in enthalpy of delta H2. This right here, as I mentioned, is your intermediate step. Okay? Where delta H is equal to delta H1 plus delta H2. All right. And of course, this is a mathematical equation. If you're asked to find what delta H1 is, obviously you can do delta H minus delta H2. That can be arranged. But this is exactly what Hess's work was all about. Okay? He wasn't able to go from A plus B to C plus D. He wasn't able to use a colorimeter to find out what this is. So he noted the fact that, oh, well, I can't always do A plus B to give me X plus Y. This is simple enough where I can get delta H. And I know that X plus Y can, react to give you C plus D to give you another delta H. So instead of going in only one step, which is ideal, exactly how I want to do it, I will have to take 2 steps to get to the same place. By getting there, all I have to do is sum up those delta H's. That is the remnants of Hess's law. So that's what he spent most of his life, of course, trying to figure out. And hey, we're going to figure this out in less than 15 minutes by looking at how do we find delta H on a reaction that we cannot build a colorimeter for. But we do know what are the intermediate steps, and it's delta H. So let's take a look at some of the rules. Now, these aren't going to make much sense until we start applying them, but let's read in terms of what are some of the things that you will encounter here. Okay, when you have a reaction and you're reversing this reaction, delta H needs to be multiplied by -1. And that's pretty, I guess, what would the word, what is the word? Obvious, I guess, that if A plus B gives you X plus Y, and that is delta H1, if you were to do the reverse reaction, it will be negative delta H1. Which means if this number was, let's say, 5 joules, let's just say 5 joules, the reverse of it will be negative 5 joules. Hope you knew that. If you don't, now you know. Number 2, when changing the coefficient of the equation, you multiply delta H by the same number. What that means is that if you have this reaction right here, let's just say, and you're multiplying every coefficient by, let's say, 3. These all becomes 3. You will have to do the same thing to your delta H. You multiply everybody by half. I don't know why you would want to do that. You will have to also multiply your delta H by half. Number 3, identical chemical on the opposite side of the reaction can be eliminated. Now, what does that mean? So let's say we were to put this whole thing together, okay? We would put this whole thing together. This is actually something you might have seen before. Okay, so A plus B plus X plus Y, I'm just grouping all of these, will give you X plus Y plus C plus D, which is really grouping these. What do it mean? What do they mean by identical chemicals on the opposite side of the reaction equation can be eliminated? What really means is that if you look at this equation right here, because, of course, these are identical, they can be crossed out. Y can be crossed out. So overall, it is exactly what you wanted. Okay? Remember net ionic equation? Yeah, similar thing that I'm trying to say. But that are the rules. So let's go. Let's take a look at example 1. Here's your target reaction. This is the reaction that you cannot build a calorimeter for. You would wish you take some ethene, which is quite combustible, by the way. This stuff shouldn't be lying around anywhere. Plus fluorine gases definitely shouldn't be lying around everywhere. Imagine you have these, and you have these, and you want to put them together. Man, I'm sure somebody's going to be knocking on your door and asking you, why do you have these in possession? Well, let's just say you want to react with these two. Let's just say you want to go through completion and get these guys. And you want to know what that delta H is. But you can't because you don't have a calorimeter that will allow you to do this safely or even at all. But you do have a calorimeter where you can perform this, and this separately. The question is, how do you turn all this information into this? In other words, how do you manipulate all three of these equations to make it look like this? Sort of like a puzzle, if you think about it. So let me do this with you. Okay, and then I'm going to leave you with a few to do on your own. So basically, you want to combine all three of these guys to make it look like the target equation. You can do a couple of things. You can flip these equations around, or you can multiply these equations by a certain coefficient. So there are many strategies. One of the strategies that I like to do first is to get what's in the target into the right side. So let's take a look at this equation right here. Because my first element that is within my interest, I guess, is C2H4. Okay? C2H4 is within my greatest interest, and as you can see in the third equation, C2H4 is on the right side. It's on the product side. But really, I want this on the reactant side. So what can I do? Well, I can do this. Instead of having this here on the product side, I can flip this whole equation around. And that's what I'm going to do. I'm going to flip this around. C2H4 will give me 2 C's plus 2 H2. I'm going to flip it around. Remember the rule that when you reverse a reaction, you have to multiply delta H by -1. So delta H3 is no longer 52.3. It is going to be negative 52.3. Okay, looking better already. Now, let's take a look at the other guys. F2 is supposed to also be on the reactant side, and it is. F2 here is on the reactant side. F2 here is on the reactant side. I think it's great. Let's take a look at the product side. CF4 is on the product side. Hey, take a look at that. CF4 is on the product side. Don't need to flip this guy. HF is on the product side. Well, I can see that HF right here is also on the product side. So good, don't need to flip this guy. Okay, so we get the flipping out of the way. Now let's take a look at the mole, the coefficient. I know for a fact that the coefficient for this is going to be good. Why? Because here I only need 1 C2H4, and here I am presented 1 C2H4. Pretty good. Pretty sick. F2. I need 6 mole of F2. But collectively, I have 2 right here and 1 right here. That's only 3. I'm going to have to somehow get 6. Now, there are many ways. I can turn all these to 4s. Okay. Or I can turn these to 2 and then turn these to 4. Oh, whatever. You get the idea. To make sure collectively you get 6. Since there are so many different ways of doing it, let's not do it yet. Let's take a look at these. See if it magically come up with 6 later on, okay? All right. Let's take a look at CF4. I need 2 CF4. By looking at what's going on over here, I see only 1. Okay, good. That's not hard to do. It's not like the other situation with F that there's 2 F's to worry about. I am going to multiply the second equation by 2. That way I get my 2 CF4. Now, just like what the rule says over here, when you are changing the coefficient of the equation by multiplying by something, you have to multiply delta H by the same number. You multiply everybody here by 2 to make sure this is 2 CF4. You better multiply this by 2 as well. You have to. That's the rule. Okay? And 680, multiply that by 2, you're looking at negative 1,360 kilojoules. All right. Hey, we took care of CF4, if you believe it or not. Now, let's take a look at HF. HF, I can only see HF on the product right here, which is good, which is very, very good. I need 4. Here, I only have 2. How do you make 2 4? Multiply by 2. Multiply this by 2. Multiply this by 2. Multiply this by 2, so it becomes 4. Remember, if you do that to the equation, you do the same thing to delta H. So therefore, you multiply 537 by 2, which will give me negative 1074 kilojoules. Okay. Wow. I told you magic always happens if you believe in magic. You want 6F2, right? Look, there's 4F2 here. There's 2F2 here. Isn't that 6? You just took care of F2 without looking at the F2. Okay. Is that magical? Now, combine all 3 of these equations. Now, usually some people write them all out, right? Collect all of these, write it out on the left side, collect all of these and write it on the right side, and start canceling. I don't like to do that. That's a lot of work. Let's cancel here on this. I know for a fact that some of these things has to go, like C's. Look at this and this. This can go. 2 C's here on the left, 2 C's here on the right. See you later. We don't need you. Okay. Now, what if there's 2 C's here and 1 C here? Well, obviously this will go, but only the 2 will go. Okay. So this 1 C will be left. But since it's not the case, there's 2 C's and 2 C's. See you later. Do you see more? Yeah, I see H2. 2H2, 2H2, see you later. Anything else? No, I don't see anything else. Because there's 1C2H4, yeah, 1T2H4. 6F2, yeah, 6F2. 2CF4, yeah, 2CF4. 4HF, yeah, 4HF. I am good. This is exactly what I'm going to do. I'm going to take delta H1, the new one, plus the new delta H2, plus the new delta H3, and I'm going to add them all up. And what I'm going to get is negative 2,486 kilojoule for every, oh, no, I don't need that, for this reaction. Okay? I cannot build a colorimeter to discover this number. That's a lot of energy. Imagine you have a couple of these things and you, for some reason, were to react those two and yield this much energy. Man, I'm telling you, you are going to be in a lot of trouble federally. Ha. That's why you cannot build a colorimeter to do this. But you can build 3 colorimeter to find these numbers out. And using Hess's law, you can discover that, oh, you know what? No wonder I can't do this physically, because this is crazy. Okay? Anyway, I hope you understand exactly what I did for this example. So let's take a look at another example. Example 2. Okay? Here it is. Oh, this one is a toughie. It's a toughie. It's not because it's hard or anything. It's because for some reason I decided to have a fraction there, just to kind of throw some of you who don't like to see fraction off. But that's just the way it is. You'll see this time to time again. Okay? The reason why you see fraction here is because we want to make sure that this is 1 mole. Okay? Because if you look at this reaction, if you just look at this reaction, it's negative 2,486 kilojoules. If I were to write a conclusion about this, I can have to say, for every mole of C2H4 that is being reacted. Or I say, for every 6 mole of F2 being reacted. Notice that's why I didn't say negative 2,486 kilojoules per mole. I didn't say per mole. Why I didn't say per mole? It's because per mole of what? For this, yeah, it's per mole of ethene, but it's not per mole of F2. It's per every 6 mole of F2. So if you want to know, hey, what's the kilojoule if it's just 1 mole of this? Well, you divide this number by 6. Then you'll know that, oh, this reaction per every mole of F2 will yield this amount. Here, there was a number there. Originally, this is 2, 4, 1, 2. Okay? The author decided that, you know what? I don't want your answer per 2 moles of AC. Okay? I want your answer to be per mole of C. So the author decided to divide everybody by 2. Hence, you have a little fraction going on here with oxygen. But that's not something that you need to worry about, because fraction don't bother you, right? All right. I do want you to pause this video, though. I want you to pause this video and figure this out on your own. And then I'm going to explain. All right. Pause now. All right, since you unpause, I'm sure you're done, right? Unless you didn't do nothing and just really wants me to tell you what's going on. But I will tell you what's going on. Right now. Tell you right now that you need to flip this. That's pretty obvious, because methanol, CH3OH, needs to be on the right side. So, to do that, I need to get rid of you. I need to say that CO2 plus H2O will give me CH3OH plus 3 over 2 worth of O2. And because I flipped this, I need to flip 676 to 676 positive. Oh. Okay. It's completely erased, so it doesn't bother you. Okay? All right. seeing the fact that you need one C here and there's one C here, you're not going to do anything with C. Two H's here, only one H is here, so that's pretty simple. You're going to multiply this by 2. This becomes 1, this becomes 2, and this becomes 2. So it's negative 484. Okay? Half of O. Well, don't need to do much here if you think about it. If you think about it, you don't have to do much here with half of O. You know why? Because there's 1 O here, 1 O here. In total, there's already 2 O2. Just writing this on the side. Let me use a different color. Okay, the combination of these two is actually 2 O2. If you look at on the right side, there's only 2 worth of O2. Remember crossing out things that are identical? Isn't 2 minus 3 halves equals a half? See? So what you have to cross out here is that 3O2 will be gone. Okay? I guess one of these will be gone. And this will end up with a half. Okay? Same thing as what we did before. It's just that not all the O2 will go because there's what, 1.5 here and there's 2 here collectively. 2 minus 1.5 is 0.5. You get the idea. You guys are a mathematician. All right, sum all of this up. Delta H will be negative 202 kilojoules. Again, 202 kilojoules per every mole of C, per every 2 moles of H2, per every half a mole of O2, depending on what you want to talk about. All right, that was a little crazy because of a little bit of fraction, but as I said, don't let these fractions scare you. All right, this one is interesting. Not only one of them you have to flip it, but you also have to flip it and multiply. Yeah, I wonder which one. And I'm going to tell you right now that you're going to figure this out on your own. I'm going to give you the answer though. That way I don't leave you hanging. I can tell you right now that delta H for this is 180 kilojoules. You tell me how. Okay, you tell me how. Same thing with this. Okay, this one is going to be difficult too. Well, not really. You have to flip one of them. I wonder which one. And one of them you have to multiply by a fraction to make it work. Oh. But I can tell you right now, the answer for this is going to be negative 129 kilojoules per every 4 mole of C or 5 mole of H2. Okay? And lastly, I'll give you an easy one. Okay, this is actually an easy one. Okay, there is a flip multiply, but there is no fraction. The answer is negative 284 kilojoules. So remember, okay, try these things out. They're like playing with puzzles. Try to get your target. And that's it. That's pretty much the first part of Hess's Law. Okay, again, the reason why these Hess's Law has been, unearthed is because there are reactions that you can't perform with a colorimeter, but you can do it stepwise because they're safer, easier to get the results through the difference in temperature. Now, again, there's a lot of reactions out there. Oh my goodness, there's a lot of reactions out there. But there are just some reaction under standard condition that you probably don't want to touch. Predominantly combustion. You don't want to find delta H of combustion of stuff. Is it hard? It's kind of hard. Is it accurate? Maybe. Is it dangerous? Absolutely. So instead of getting a colorimeter and find out the combustion of stuff, there is this in the IB booklet. Chapter 12 and chapter 13. We will talk about these numbers in the next lesson, because these are numbers that got discovered by scientists who actually went to investigate these guys. Like, for example, here, CH4, methane. This guy has a delta H of formation, which I will talk about soon what that is, of -74 kilojoules per mole, meaning that per every mole of methane, you yield that much energy, because it takes that much energy to make. So it takes that much energy that gets released. All right, so we'll talk about this in the next class. But in the meantime, try to see if you can get to the answer that I got, and we'll take it up next class. Bye, guys.